Belgium. And I think this shows in his red circle here. And he's gonna tell us more about the electronic structure of polyethylene and also graphene nanoribbons. So let's welcome Professor Deleuze.
First of all, I would like to thank Professor Yongda Chai for having invited me here at National Taiwan University. The purpose of this travel is to establish a collaboration which I'm sure will be very fruitful in the forthcoming years. Thus, I come from Belgium, which is in the heart of Europe, as you can see, between France, Germany, and Holland. And this is a map of Belgium. Thus, this is where my university is located, Hasselt, in the northeast of Belgium, something like 100 kilometers far away from Brussels. As you can see, this is located in the Dutch-speaking part of Belgium. In the south of Belgium, we speak French. I'm living myself in this area, because I'm French talking, as you may hear from my accent, and thus every day I commute and I go working in the Dutch-speaking part of Belgium. Sometimes this makes my life a little bit complicated, but so far I can manage with it. The title of my talk will be In Pursuit of the Electronic Ground State and Properties of ACs and Graphene Nanoribbons at the confines of non-relativistic quantum mechanics. This is a very long project which started something like 12 years ago. At the time we had a collaboration with an institute for microelectronics, and they were very much interested in the electronic properties of pentacene, a compound which is used for the making of organic thin films with extremely large charge carrier mobilities. To understand the properties of these systems, we had to calculate the electronic structure, the ionization spectrum, and related properties like electron ionization energies or electron affinities. So this is how this story started. Thus in my talk I will basically discuss two main topics. Thus in the first part we will focus on benchmark calculation of ionization energies, electron attachment energies, singular triplet excitation energies, and electric dipole polarizabilities of ACs, using the principles of a focal point analysis of energy differences. That's what we want to get are the most accurate possible reasons. Thus we want to get right numbers for the right reasons. And as you will see, a quite logical extension of this will be to discuss the half metallicity of graphene nanoribbons. And as I will show to you, this is more a new quantum mechanical Eldorado for nanotechnologies or a high-for-matter scientist. Actually, as we will see, half metallicity, basically, as it is defined today, is a methodological artifact. Thus the basic idea is the following. Thus we want to go to the full CI limit in conjunction with an asymptotically complete basis set, which should represent the exact solution of the Schrödinger equation. And thus in this purpose, we have to proceed through a dual extrapolation. Thus we have to do calculations with improving basis sets, and at the same time with improving treatments in correlation. And thus by combining pairwise results obtained at different level and using different basis sets, we can extrapolate results to a full CI limit in conjunction with an extremely large basis set. In addition, we use well-established procedures for extrapolating results to the limit of an asymptotically complete basis set, using Dunning's correlation consistent polarized variance basis set of double zeta, triple zeta, quadruple zeta, pentuple zeta quality. Thus, this is the so-called further extrapolation, which enables us to extrapolate Hartree-Fock energies to this limit. And this is the formula we use from Schwartz to extrapolate correlation corrections to the Hartree-Fock energies. Thus, we use different kind of combinations. Thus, for instance, in this acronym, FPA-QZ, thus we proceed for focal point analysis. Thus, at the QZ level, thus we extrapolate MP2 corrections to the limit of an asymptotically complete basis set using CCPV-DZ, CCPV-TZ, and CCPV-QZ basis set. And then on this, we add differences obtained in between MP4 and MP2 energies using a triple zeta basis set. And then on top of that, we add energy differences obtained using couple cluster SDT theory compared with MP4 theory in conjunction with the double zeta basis set. Thus we have different levels here. We use A here to emphasize that we include that we use augmented basis set, including diffuse functions. But okay, I will not describe all these acronyms in detail, but the main principle is always to combine different level in theory so that we can go very close to the full CI limit in conjunction with an asymptotically complete basis set. So this is the starting point of the story. That's a quite old paper now, which we published in 2001. And we computed the ionization spectrum of pentacene using the so-called ADC-free approach, which was developed by Professor Zederbaum and his co-worker at the University of Heidelberg in Germany. But this is a very powerful approach, which enables to calculate ionization energies at third order in correlation, and also shake up ionization energies through first order in correlation. Thus here you have all the lines we computed. Thus the line are given the spectroscopic pole strength as a function of the binding energy. When we have a spectroscopic pole strength close to 1, this means that we have a 1 electron ionization process, which is consistent with the Koopman's theorem picture. But here you can see that at larger binding energies, we have many lines corresponding to shake-up states, which are electronic excited states of the cation. This corresponds to so-called two-hole, one-particle configurations, thus corresponding to 1 electron ionized plus 1 electron excited. Thus here, the orbital picture of ionization completely breaks down. Well, you can already see that the lowest shake-up line appears at 8 electron volts, thus in the outer valence region. This is a satellite of a pi orbital, and thus this is very surprisingly low, and this indicates altogether how easy it is to excite electron in a compound like pentacene. Thus this already gives a quite clear indication that pentacene is a strongly correlated system. The problem we had, that's when we compare experiment overall, we had an extremely good agreement in reproducing the position of bands, except for the line corresponding to the HOMO. Thus at the ADC-free level with a small basis set like 631G, we had 0.9 EV disagreement, which was far too much to be acceptable to us. We wondered what was the reason for that. And thus we carried out computation using a larger basis set, using the so-called outer valence Green's function method, thus which also enables calculation of 1 electron ionization energies through third order correlation. And thus, when we compare result experiment, basically we see that the argument deteriorates with increasing system size. Thus, for a system like pentacene or hexacene, with a basis step like CCPV-DZ, we get 0.5 electron volt disagreement, which is very strange, because usually autovariant Green's function method and ABC-free method are known to give ionization energies within 0.2 electron volt accuracy. Because at that time, it was completely unclear to us whether this problem was due to the basis set, which is already quite large, or due to the method, so to an insufficient treatment of electron correlation effect. So that's why we decided to go to the full CI limits in conjunction with a complete basis set. And so these are the results we got by means of a focal point analysis for acenes ranging from benzene up to hexacene. Thus we computed first the vertical ionization potential. Then on top of this, we added relaxation energies. As you can see, relaxation energies decrease with increasing system size. And then also on top of that, we added 0-point vibrational energy corrections. Thus adding these corrections to our best estimate for the vertical ionization potential, we got this value here. And as you can see, compared to the best experimental value, we are extremely close. We are within 0.4 electron volt, which means that we have reached so-called chemical accuracy, which means we have reached 1 kilocal per mole accuracy. 1 kilocal per mole is equal to 0.04 electron volt. So when analyzing these results in detail, we found that the Hartree-Fock estimates for the vertical ionization energy converge extremely fast with respect to the basis set. But the effect that dominates at the second order correction obtained at the MP2 level, but these show a much slower convergence with respect to the basis set. We also found that the smooth and faster conversion of the higher order corrections with improving basis sets justifies the principles of the focal point analysis. And and the basis set dependence of the many Body corrections to the vertical ionization energy rapidly increases with increasing system size. This was quite a surprise to us, because this means that if you want to get accurate results on A-scenes, large A-scenes, well, the basis set is probably one of the most important elements. Thus, if we go to the limit of an asymptotically complete CCPV infinite Z basis set, we found that the third order treatment would ensure an accuracy of something like 0.15 electron volt. Because the problem we had previously with the ADC3 method was not a too approximate treatment of correlation, but this was rather due to the fact that the basis set we used was too small. Thus, we also found that structural relaxation effect and the P corrections limited, and they decrease rapidly with system size, and this is quite clear. This is because the orbital we ionize is delocalized on larger and larger region in space. And then we found that by means of this FPA treatment of adiabatic ionization energies, it was possible to reach chemical accuracy, just 1 kilocalorie per mole. That means 0.04 electron volt. In the next step, just a few years later, we consider computation of the vertical electron affinity of any scenes. Because I give here an example of anthracene, and this table shows how a focal point analysis works. Thus, you see that the Hartree-Fock estimate of the vertical electron affinity converge quite fast with the basis set. On the other hand, you see that the amplitude corrections converge much more slowly with respect to the basis set. The corrections obtained at the MP3, MP4 couple cluster SD and couple cluster SD parenthetical T level are much smaller, and so this way we can extrapolate these results to larger basis sets. And thus by combining all these results together, we can obtain these estimates for the vertical electron affinity of anthracene, and thus the best result we get is 0.28 electron volt with this method here. Thus, including diffuse functions does not make really a big difference in this case. This is because anthracene has a bond anionic state, and thus if we include diffuse functions, we also get 0.28 electron volt as the best estimate of the vertical electron affinity of anthracene. So this table summarizes the results we got for A-scenes ranging from benzene until hexacene. Also for systems like anthracene, naphthacene, pentacene, hexacene, well, it doesn't really make a difference if we include diffuse functions in the basis set. Thus, in this case, well, we have a quite fast convergence. On the other hand, the situation is much more problematic for benzene and naphthalene, and this is because these systems have negative electron affinities. This means that the electron in the anion isn't bound. And in this case, there is a very strong dependence of the results on the inclusion of diffuse functions in the basis set. Thus, actually, this is a very difficult situation, because if you think about it, if you have an unbound anion, the electron lies above the zeroth of energy and wants to escape from the molecule as far as possible. Thus, if you would put more and more diffuse functions, ultimately you would get a vertical electron affinity which is strictly equal to 0. And this is not exactly what we see in electron transmission spectroscopy measurements. In these measurements, an electron is coming in, is temporarily trapped around the molecule, and then it escapes, it decays away. Thus, in order to get results that fit with experiment, somehow we have to confine the electron in the region that surrounds the molecule. And in order to do that, in this case, we have to deliberately remove diffuse functions from the basis set. And if we do that, this is the results we get here. Minus 1.50 electron volt for benzene, and minus 0.48 eV for naphthalene. Because these results in blue represent our best estimate for the vertical electron affinity of A-scenes. Let's compare experiments. Well, we get pretty good results, provided we also include corrections for 0-point vibrational energies and geometrical relaxation effect. And as you can see, for all systems, including benzene and naphthalene, we managed to produce the experimental value within chemical accuracy, thus 1 kilocalorie per mole. This means something like 0.004 electron volt. So the reason why we have to remove diffuse functions from the basis set can be understood from these slides. Because here we put the electrostatic potential energy map for an external electron, and we compare it with the LUMO of benzene and naphthalene. And as you can see, the LUMO of benzene and naphthalene coincide with a region of space that is electroattractive. And this region of space is surrounded by two electro-repulsive barriers. Because an electron coming in will remain temporarily trapped here before escaping again. And thus it remains a sufficiently long time here so that it can also experience the effect of vibrations and geometrical relaxation. Because in this sense, what we see in electron transmission spectroscopy measurements at what we call pseudo-adiabatic electron affinities, those adiabatic, those electron affinities corresponding to a slow timescale process, but not infinitely long timescale process. Just to summarize the results for this section, this again we've found that the smooth and faster convergence of higher order corrections, the copper plus the SD and copper plus the SDT corrections with improving basis sets, justifies the principle of focal point analysis. Thus benzene and naphthalene were found to be quite difficult case, because in this case the unbound nature of the anion implies that the adiabatic electron affinity is, well, this doesn't work anymore. Okay. Yeah. Does this implies that the adiabatic electron affinities vanish in the limit of a complete basis set? On the other hand, there are no problems with the anions of anthracene and larger because these anions are bound, and thus the convergence of the FPA treatment of electron affinities can be quite easily reached within chemical accuracy, regardless of the presence of diffuse functions in the basis set. As for benzene and naphthalene, we have seen that diffuse functions must be removed from the basis set in order to enforce confinement of the extra electron in the molecular region. And this is because the pi star region corresponds to an electroattractive region of the molecular electrostatic potential, which is surrounded by sufficiently high energy barriers against electron decays. And thus, extrapolation to this basis set, CCPB infinite Z, appears to compensate the limitation of the basis set, and thus we can also, in this case, achieve chemical accuracy. But in this case, for benzene and naphthalene, thus the measured electron affinities should therefore be regarded as pseudo-adiabatic estimates, thus corresponding to a finite but long enough time scales with respect to nuclear motions, thus vibrations, thus a time scale of the order of 10 minus 12 seconds. Then next we considered the vertical singlet triplet gap of acenes. Thus we see that for these properties, including diffuse functions, does not really make a big difference. And you can see that, well, with respect to the different level in the treatment, there are not much variations, but still in this case, we can also achieve chemical accuracy, thus an accuracy of 1 kilocal per mole. Thus again, to compare with experiments, thus we have to include relaxation corrections and 0-point vibrational corrections to our best estimates for the vertical singlet triplet energy gap. These are the values we get compared with experiments. Well, in this case, we have agreement of the order of 3 kilocal per mole, well, which is not that bad if you think that on the experimental side, most of these values have been obtained in Glasser matrices. Thus we should also take into account the effect on the environment. So all calculations were for the gas phase. On the experimental side, these values are subject to environmental effects. Thus in this case, for the singlet triplet energy gap of acenes, thus again, the delta R34 estimates converge extremely fast with respect to the basis set. Again, we find that the amplitude correction dominates and converges much more slowly with the basis set. Again, the faster convergence of high order correlation corrections with the basis set justifies the principle of the determination of these energies within chemical accuracy. Again, structural relaxation effect and ZP corrections are limited and decrease rapidly with with system size, and single triplet energy gap appear to decrease monotonously with increasing system size. Then next we considered computation of the electric dipole polarizabilities of naphthalene, anthracene, and tetracene. Thus, these properties can be calculated from second-order energy derivatives with respect to an external static electric field. And thus what we did here is that we estimated these energies according to finite field calculation, again according to the principles of the focal point analysis. And thus to simplify the calculation, we made use of the standard molecular orientation so that all of diagonal components of the polarizability tensor identically vanish. So on this side you see the results we obtained for naphthalene. Well, you see that the results depend quite strongly on the basis set and they converge smoothly with increasing basis set. Well, there is a quite strong variation from R34 to MP2 level, and also, well, it appears that the triple excitations at the CCSD level make quite a substantial difference. So on the next slide we have the results obtained for anthracene. You see that the triple excitations make a quite strong contribution and that their extent tends to increase with system size. Because it is clear that if you want to compute polarizabilities within a few % accuracy, well, you need to have very large basis set, and you need also to take into account parenthetical triple excitations into account. Thus, we found a smooth convergence of the result with respect towards the limit of a complete basis set. And also the basis set altogether appears to be the factor that dominates the quality of the computed polarizability. So these are the results we obtained for naphthalene compared with experiments. Thus, we have extremely good agreement with data, experimental data obtained using laser Stark spectroscopy, as you can see here. Thus, for the isotropic polarizability tensor, we have an accuracy of 1 or 2%. The same for anthracene. You see that for the isotropic polarizability tensor, we have an extremely good match with the experimental value. Thus, in the case of anthracene, well, it appears that diffuse functions appear to make quite substantial difference, which was not the case for naphthalene. Thus, these are the results we obtained for tetracene. Thus here we had some convergence problem in finite field calculations when diffuse functions were included in the basis set. And also we could not compare with any reliable experimental data. Well, in the literature we found an experimental value of 218 atomic units, but the origin of this value was totally unclear. But nevertheless, it seems to compare quite well with our calculations. To compare with experiments, we should also take into account thermally induced vibrations. And to do that, we performed molecular dynamic oscillations using the BOMD scheme, the Born-Oppenheimer molecular dynamics. We did this using the omega B97 XD functional by Professor Chai, along with this basis set. Thus, with this approach, we can calculate the effect of the Thus, we can compute the average polarizability and compare it with the result obtained at equilibrium. Thus, from this, we can make an estimate of the correction due to the vibrations induced by temperature. We add this to a best FT estimate, and this is the value we get, and that we can compare with experiment. And as you can see, for naphthalene and anthracene, we've managed to obtain relative accuracies of the order 1.2 to 3.5%, which I think is quite remarkable. So to summarize this section on polarizabilities, thus we have found that the basis set dominates the quality of the computed polarizabilities, and diffuse functions were found to be essential in the case of anthracene. Also, calculations of at least CCSDT quality along with BOMD estimates of vibrational corrections, are required for obtaining results within a few % accuracy. Then the next question that arises upon revising the literature was the very controversial nature of the electronic ground state of NACs. There is a huge debate in the literature about this question. Is the electronic ground state of this system a singlet closed shell or a singlet open shell electronic ground state? And this arises because when we do unrestricted DFT calculations, we observe asymmetry breaking of spin orbiters, as you can see here in the case of FSC. There's been a lot of dispute in the literature because it appears that the first open shell singlet ground state in the series of ACs depends very much on the functional, depending on the functional, hexacene, heptacene, or even octacene were reported as being the first open shell singlet species in this series. Also, another problem we have is that if you look in the literature, there is, in my opinion, no clear definition of what an open shell system is. If you speak with Professor Ernest Davidson, the editor of the Journal of Chemical Physics, he will tell you that the idea of a singlet open shell system is a complete mathematical nonsense that cannot exist. Well, for some people, singlet open shell, this means that we have a symmetry breaking of spin densities in spin unrestricted Hartree-Fock or DFT calculations. For our people, singlet open shell species means that we have deviations of natural orbital occupation numbers from 0 and 2 in multi-reference calculations. This is, for instance, the case of Professor Hans Lichka at the University of Wien. But really, nobody so far has provided a unique and objective definition of a singlet open shell species. Just to make clear the sequel of my talk, what I will call an open shell singlet species is a species in which we observe asymmetry breaking in spin densities. Well, it appears that the onset of the symmetry breaking of spin densities in symmetry or unrestricted calculations depends very much on the fraction of Hartree-Fock exchange. Because if you do a calculation at the Hartree-Fock level, even benzene is a singlet open shell species, which is completely contradictory with common knowledge. If you decrease the fraction of Hartree-Fock exchange to 43%, like with the MPW1K functional, then the onset of open shell singlet species in the acene series is naphthacene. And then if the fraction of Hartree-Fock exchange decreases, then it becomes hexacene, heptacene, or even octacene. Thus, this already indicates that there is something wrong with the idea of singlet open shell species, that this is basically due to some methodological problem. Well, if you look, on the other hand, at the composition of a CAS wave functions, that's obtained from such calculation here, just using an active space of 14 orbiters with this basis set and geometry, we find that with increasing system size, indeed, the weight of the first CI coefficients in the CAS wave functions decrease with increasing system size. Because for a system like pentacene, the highest contribution corresponds to 0.5. This shows that the extent of multi-reference character increase indeed with the size of the ACs. And this is consistent with calculations by Professor Child. The same if you look at natural occupation numbers, where you see that depending on the size of acene, well, there is progressive deviations from 0 and 2, and you see that for systems like heptacene, octacene, monacene, and dicacene, that we go progressively to a singlet open shell species, thus with a quite pronounced multi-reference character. So, to summarize this question of the controversial nature of the electronic ground state of ACs, the main problem, the main issue is that unrestricted variational treatments may result into symmetry broken and unphysical solutions because the Fock operator in SCF calculation